Hi everyone and welcome to the new video. In my previous project I explained how to use an ESP32 and now we can do some fun stuff. We can play some music. Once I saw a review of the Stylophone, a vintage music synthesizer made in the 60s. It was popular at that time and it is still available today. In this video we will make a similar project and we will make a real music synthesizer based on ESP32 and the modern hardware. I will show how to choose the components, how to write the code, and how to make a professional-grade PCB. Without further ado, let's get into it. Before we begin, a small note. This project was inspired by the Stylophone, but it has no relation with the original one. If you want to find an original Stylophone to play, you can easily find it in Google. And here we will make a new project from scratch. We will use an ESP32, an audio interface, and we will code it. Without further ado, let's get into it. And as a first step, let's make a list of components that we will need. This is a hardware and a software project, and obviously we will need some hardware. And the brain of our system is an ESP32. It's a so-called system-on-chip controller. It is pretty powerful for its size. It's a dual-core 32-bit controller with about 500K of RAM. It has a CPU frequency of about 200 MHz. It may sound not impressive for today's standards, but we shouldn't forget that in the 90s it was parameters of the high quality of digital audio workstation, and now we can get a pack of 3 boards for only $10. The second component of our synthesizer is an E2S chip. The ESP32 board cannot directly drive a speaker because it will not have enough power for that, so I am using E2S interface to generate the sound. The protocol itself is pretty complicated, but the library is doing all the job for us. We only need to generate audio samples and the chip will make the sound. I will be using this board, and as we can see it has a connectors to the speaker and it has a connectors to the ESP32 board, so technically it is easy. Then I will be using one of the ESP32 inputs for the volume control. As explained in the previous video, we can read analog values with an ESP32, so we can use it to adjust the sound. And probably the most important part, we will need keys to play the music. I will be using the same idea as in the Stylophone. I will need to press the key with the stylus to generate the tone. And obviously I need to configure ESP32 pins as inputs. As we can see, ESP32 has a plenty of pins, but not all of them can be used as an inputs. For example, some pins are reserved for ground or for power. So in general, with an ESP32 I can have about 1 octave range or about 12 keys. This is enough for the first version and we can play some melodies. In the second revision I can use a GPIO extender so we can have more keys. If you want to see this version, write in the comments below. Now I will show the schematic, then we can start writing code, and then I will show how we can make a professional grade PCB. Okay, now I will show the schematic. I'm using a KiCad editor for that. It is good for the project like this because I can not only draw the schematic, I can also make the PCB here. And as you can see, the brain of this project is ESP32, it's located in the center. I was not able to find the proper KiCad model for that, and I was going to use a connector anyway, so I am using a left connector and the right connector. I also added an LED to show the current playing mode. For example, it can be sine wave or triangle wave or something else in the future. I also have an input button to change the mode. And I also add an extra button that can be used in the software for the future. There is also a potentiometer to change the volume. All other keys are actually used for playing. As I explained before, there are about 12 of them. Some input pins on the ESP32 have no pull-up resistors, so I added them manually. You can find these pins in the ESP32 description. And there are also 2 ground pins that are using to connect the stylus. This is the connectors for the sound interface. As I explained before, it needs only power, ground and 3 data pins. And technically that is it, this is all the board. As we can see, the design is pretty simple. At the end of this video I will show how to make a professional grade PCB with KiCad, and now we can start coding. Okay, now we can open the Arduino IDE and start coding. Even if you don't have a PCB, it is not a problem, you can just use a breadboard. I was testing my first version on this breadboard and it was working well. You can just connect all the buttons and all the wires. As a first step, I will import the files for the audio interface. We will use it to generate the sound. As we can see, I am using 3 pins. Then I will add definitions for our I/O ports. And now I will create an array of the piano keys. NP means no pull-up. As I mentioned before, some pins on the ESP32 have no pull-up resistors. It is important to know because the code is a bit different. As a next step, I will create a list of key states and the key frequencies. To play the note, it is important to keep the phase, otherwise they will be clicking sounds. And also it allows us to play several keys at the same time. And I also have a list of all key frequencies, which allows us to play the notes. Also, there was a typo here. The K pressed array should have an integer type, of course. Now I'm creating the variables for the audio interface. As we can see, we're using I2S protocol. As we can see, the key frequencies are not very high, so it is enough for us to use sample rate 11 kHz. We need to calculate the audio using sine or cosine wave, so it makes calculation easier if we have a lower sample rate. Now I am adding the play mode. I set the variable as a volatile because I can change it in the pin handler. And this is our main definitions, and now we can start writing code for that. In the setup method there are three main blocks. Serial is used for debugging. When the code is ready we can remove it because on the real board maybe there will be no serial connection, but for debugging it is nice. And here I am initializing I2S protocol and I am initializing the pins. And just for debugging I am printing the message app started. The setup I2S method is easy. I only need to set the pins, and only if the chip is not found then it can start, of course, because our board cannot work without audio. As a next step, let's implement the setup pins method. Here I have my LED. I will also initialize the pin mode as input for the button, and I have a range up key. It is also input. And this is the volume. For volume I use analog read, so I can read the state of the potentiometer. And here are the keys that will be used for the piano. And here I initialize all the keys, and as we can see I set it as an input with a pull-up enable. But there are some keys, these pins don't have internal pull-ups, so I use only input without input pull-up. This is only difference. Now let's see if we can compile the code. As the next step I will create a method update keys. As we can see, this method is pretty simple, it's not a rocket science. I use a digital read method to read the key, and if the key was pressed then the state is changed. First I tried to subscribe to the key change, but for some reason it didn't work for this board. Because ideally we don't need this, ideally we can just subscribe to the pin change, but for some reason it does not work, and I read on the Stack Overflow that it can be a hardware issue. And these two methods, on-K down and on-K up, they are actually simple. When the K is down, I set the phase to 0, so our sound will start again. The next important method is update volume. As you remember from the schematic, I am using analog read to read the potentiometer. It is connected to the ground and to the power, so when I rotate the knob, its value is changing from 0 to 496. And I am using 60-bit sound, so I need to adjust this value. I multiply it by 4. As we can see here, updating the volume is easy. Now we can also update the mode key. This is a bit more tricky, but it's also not a rocket science. The problem with reading the keys is that sometimes when you press the button, several events can be generated because buttons are not ideal. To overcome this, I set a threshold to 500 milliseconds, and I remember the last press time. As we can see, it is a static variable, so it presented in the memory. And it allows us to prevent the case when we press the button and we get many events. As a reminder, I have several modes here, so I'm just switching it one by one. Okay, at this moment we have implemented reading the keys, and now we're ready to the fun part. Let's play the audio. First I will show the general idea how it works, and then we can add real notes. As a simple example, let's say if we have a variable, it is a global variable that is keeping the phase. And the general idea is simple. I have a frequency that I want to play, I have an amplitude, as an example it is hard-coded to 10,000, and then we can just calculate the value using the sine function. And the important part is here, we have a phase increment that is calculated from the frequency. As we can see, it is a simple formula. And what I'm doing in the last part, I'm updating the phase. If you remember the school geometry, the sine or cosine wave has this range. And as a final step, I can just send this data to my audio device. And technically that is it. This is how we can generate the tone. And what I can do now, this is my main loop. This function is executing infinitely. And after updating the volumes and updating the keys, I can generate the sound. Of course, as we can guess, when we run the app, it will play this sound always. As we can see, the code is pretty simple, and now let's run it and see how it works. It is important to know that this function works always, so it will be always generating this sound. There is no keys processing yet. And now we can hear the sound. Now I will disable it, otherwise it's too annoying. It is important to know that this code is actually running at real time. My sample rate is 11 kHz. All my code must be executed faster, otherwise there will be clicks in the audio and it will sound not very good. And for example, if I want to blink the LEDs, I cannot just use something like delay 1000, because otherwise there will be no sound at this moment, because this function must be called. It is important to know that all the code must be asynchronous, it must not break this loop. So I must send the data to the chip every 11 kHz. And now, while we understand how it works, I will show how to play the real notes. As you remember, I already have a key phase array, and I also have a key frequencies. So as you can guess, now my code is pretty simple. I only need to change this function. I will remove this. I don't need this part anymore. Instead, I will just use all my keys. So now I changed the code, and as we can see, the idea is the same, but now I have a loop through all my keys. If the key is not pressed, then I skip this part, and if the key is pressed, then I take the frequency from my array. So technically this is the same code that I used to generate a sine wave, but the difference is that I'm doing it for all the keys. So as a bonus I can play several buttons at the same time. And generally that is it. Now I can upload it and see how it works. As we can see, our main loop consists only from 3 methods now. And interestingly, I did a test with an oscilloscope, and it turned out that update volume works slower. Interestingly, this analog read method is very slow. It uses a special analog to digital converter, which needs some time to calculate this analog value. But why I use it here? Of course, I can optimize it. I can read the volume, for example, only when I press the key down. But the thing is that some musicians want to change the volume during the playing. For example, if you press the note and at this time you change the volume. So it is important to update the volume in the real time, not only when the key is pressed or released. So now let's upload this and see how it works. Now we should be able to generate the real music. And now I'm pressing the button and we can hear the sound. If you listen carefully, you can hear the clicking sound at the end when I release the key. It happens because we generate a sine wave, and when we interrupt it there is a click. I will show how to fix it later, but now let's go forward. And as a next step I will show how to display a heartbeat LED. First I will create a function show heartbeat LED. As a reminder, we have a limitation, we must not block the main loop. For example, if you are a beginner and you want to blink the LED, you may write something like this. But as I explained before, this approach doesn't work here because we have a real-time application, and this function generate wave output, it must generate data always, otherwise the audio will just stop. If you are a beginner, it's tempting to do something like this, but this approach will not work, so I will delete it. Instead, I will remember the time when the function was called last time. And the logic here is simple. If 1 second passed, I turn LED to on, and when 2 seconds pass, I turn the LED to off, and I remember new time, so this loop will repeat. And as we can see, when this function called single time, it will not be blocked. So this is what we want. And let's see how it works. Now I can add this function to our main loop. In the future I will add several modes here. For example, when it is a sine wave, we can make short blinks. When it is a triangle, we can make double blink or something like this. If you have other ideas, write in the comments below. I will be curious to know, but now let's see how this works. Let's compile it and run again. And as we can see, the LED is blinking. As we can see, our code works. Let's go forward. Okay, at this moment our code is working and I will show how to make a PCB. As we will see, it is not a rocket science and it is easy to do it. As I mentioned before, I am using KiCad for the project because it is a convenient tool. We can not only draw the schematic, we can also make a PCB here and then we can order it for production. I will show it as well. Sometimes, as I mentioned before, the challenge is that not for every component there is a library. For example, there was no library for ESP32 and I was just using a connector because it was easier to me. When the schematic is ready, we need to assign the footprints. To do this, I am opening the menu and selecting Assign Footprints. Here the idea is that we have a component and for every component we need to have a footprint. We can select footprints from the library. For example, this is a large socket and we have a connector like this. Of course, for our project, the tricky part is to create piano keys. I created it separately using the footprint editor. I will show it as well. Here we can see how our keys looks. I will close this window now. I will also show the footprint editor because this was a tricky part here. For example, I created this component for the speaker. Piano keys I created manually. It is also easy. You just select the primitives here and you can just draw. For example, this left component is a line. Here I created a pad which is used for our electric connection. And here are all my keys. As we can see, we have a left key, we have a right key, and etc. So technically it is easy. The tricky part for the key is to remove the isolation mask because we need to touch them with the stylus. Technically how it works, I need to select the mask. We can see it's this one. And I need to draw the area where the mask should be removed. So it's like negative, it's like inversion. And when all components are done, I can draw a PCB. Now I can switch to the PCB editor. Of course, I am not showing all the process step by step, it will be too long, but this is the general idea. You can press the components and you can draw the wires, and here it is, here how it looks. Important part here is a 3D viewer, so we can see how the board looks. For example, for this board it looks like this. This is a 3D viewer. As we can see, it is a pretty good render, so I can see my board, how it looks. These are my connectors that I included. This is the LED. Of course, the colors are not accurate. For example, this is not an ultraviolet LED. And this pin will be not like this. Here will be just a button, but technically for us it does not matter. We only need to have a hole here. So we can preview our board. We can preview it from both sides. We can verify that everything is correct. When you are making this design, the ruler is your friend. For example, when I was adding ESP32, I must be aware that this distance is correct. And now I will show how to send the PCB to production. Okay, when our PCB is ready, we can order it. And for this project, I will be using a PCBWay company. The process of making the board is surprisingly easy. You export the Gerber files from KiCad, you upload it to the website, and 24 hours later it will be shipped. Let's see how it works. First I need to enter the dimensions of the board. As we can see, the minimum quantity is 5 pieces, which is okay. If something is wrong, we have a backup. As a first step, I need to upload the Gerber files. As we can see, it detected all parameters automatically. Here we can verify all settings, and here we can change them if needed. As we can see, we can customize a lot of things, but I will keep it all as a default. As we can see, the production itself costs $31 US. We also need to select shipping. I live in the Netherlands. For you, it probably will be different. For example, DHL costs $25 US and so on. As we can see, the standard global shipping is the cheapest one, and it will take 7 business days. And of course, in many countries, you also need to pay an import tax. Here I must confirm that I'm not making the part of the weapon. And here is the order I created. We can also see the details. Out of the camera I created an order, and with the magic of the video you will see the result right now. Okay, sometime later a package has arrived, and as we can see the packaging is good. After checking the board I have found one issue that I forgot. By default all the board is covered by the isolation mask. To play the music I need to touch the key with the stylus, and obviously with an isolation mask it will not work. I already fixed it in the KiCad project, but this board was already made. Such a mistake could be a disaster in production if there is 1,000 of boards, but for one board I can just change it manually. I will just put a piece of the copper foil on each key and it is enough for the fix. So technically it is easy. Originally I was going to show the soldering process, but this video is already long, so I will just do it out of the camera. The board quality is good and it is easy to solder it. Okay, out of the camera I prepared the board, and here are the components. On the top right side is the ESP32, then we have an audio chip, we have a speaker, and I also added a piece of the copper foil to every key so I can get events in the software. I also soldered 2 buttons that I can use in the software. Hopefully there will be no magic smoke. Let's connect the board and see how it works. Okay, as we can see the hardware works fine, but there is one improvement that I was going to make. I need to remove these annoying clicks that we can hear. Technically the problem is here. We have this loop where we generate the tones, and as we can see, if the key is not pressed, we immediately stop playing, which causes the clicks because the sound is just broken, and I will show how to fix it. So our task here is to gently release the key. First I will add key states, so I will have a key idle, key press and key released. Here I will add 2 arrays, key state and the key amplitude. When we have a key up event we set the key to release, and when the audio is gone then the key will go back to idle. I will show now how it works. As the first update I will reset the key phase only if the key is in idle state. And then when the key is down, I set the state to key pressed, and I also set the key default amplitude to 1. And the next update will be in the key up handler. As we can see, if the key state is pressed, then I switch the state to the key released. And the last update will be added into the generate wave output. Now I will be using a key state. First I put a value to a separate variable so I can change it. And now I'm adding an extra block of code. If the key is released, then I slowly decrease the amplitude. As a reminder, in onKDown method the default amplitude is 1. So if the key is released, I slowly decrease the amplitude. And when finally it goes to 0, I set the key state to idle, and technically that is it. Of course it can be optimized. In the future it can be a separate constant like decay time or attack sustain release. We can implement the full envelope, but for now it is good enough for the first version. In the future I will update it. If you want to see more updates, don't forget to subscribe. And now let's see how it works. And as we can see, it works. In the future I will implement a full envelope, so we will have an attack and release, but for now it works good. As we will see, our system is very flexible. Just for fun I will show what will happen if I will increase the time interval. By making this constant smaller I can make a delay longer. As we can see, we have this effect of the tubular bell sounds, and this is fun to see. So as we can see, this system is very flexible. This was the first part of the video and we can do much more. And that is it for this first part. As we can see, lots of things can be implemented. This video is already long and I will implement different audio modes, for example sawtooth or triangle wave. I will do it in the next videos, so stay tuned and press like and subscribe to see more videos like that. I will put the project on GitHub, so you will be able to download it. If you want to improve it, feel free to get the project. If you have some nice ideas, feel free to make a GitHub PR. And if it works well, I will merge it as well. I will make this project open source so everyone can participate. The PCB is also added to the project, so you can send it to production as well. You can use PCBWay or any other service. There are lots of services where you can send the Gerber files and get a PCB by post. So feel free to play with that, feel free to test the board. I hope it will be a cool project in the future and we can do more improvements. That was it for this first part. Feel free to press like and subscribe if you enjoyed it. Thanks for watching and see you next time.